We just looked at the first quiz answer scripts. I am generally happy because people did reasonably well, excepting that two questions which I thought people could have done better. First question was about an expression to find out the miscibility gap, the temperature at which the miscibility gap closes. In fact, there are only three who have done it correctly. One is Vijay Lakshmi, Prerana, Raghu Kiran. Very happy to see these three doing it right. Rest of them basically try to equate what we are talking about is miscibility gap. I want to do this today so that we are looking at this phase diagram and we are interested to find out this. What is the temperature at which the miscibility gap closes? That means a temperature above which you have single phase alpha, below which you have alpha 1 plus alpha 2. If you look at the what is called the free energy composition diagram at any temperature within the miscibility gap, we know that the free energy composition diagram looks like this, something like this, and we can talk of a common tangent, and these 2 points are what we call them as binodals, and if this is done at room temperature, these 2 points basically corresponds to these 2 points, right. We said that, and we said at temperature something like this, the same free energy curve would look differently, and if you draw it once again, the free energy curve looks something like this, right. So that means there a single phase is stable, whereas here a single phase is not stable, it splits into 2 phases, and that brings us to 2 more additional points which we discussed, which we call them as spinodal points. And in principle, whatever we are discussing here, the temperature for miscibility gap closure is also the temperature at which the spinodal closes, obviously, because if I draw a spinodal curve with a different color, let us say chemical spinodal, mind you, I am not talking of coherent spinodal. If I draw a chemical spinodal also closes at the same temperature. So in principle, whatever temperature that we are talking about, the temperature at which of miscibility gap closure where the miscibility gap ends is same as where the spinodal ends. What we call is the critical temperature for the spinodal decomposition, a temperature below which you have the spinodal occurring, and what is the maximum temperature where the spinodal can occur is this temperature below which you can see. In fact, for every alloy there can be a different spinodal temperature. Similarly, for every alloy composition there is a different temperature at which the miscibility gap is no more there. But if you look at where is the maximum usually comes at 50-50, provided we assume that the system is a regular solution model. That is what this question also clearly says, assume that the system is following a regular solution model. The moment you assume that it is following a regular solution model, then we know the delta H mixing is omega XA XB, and this omega XA XB is a symmetric function. If I plot the omega XA XB, if the omega is positive, then delta H mixing will look, if somewhere I have sorry, if somewhere I have a 0 here, the delta H mixing would look like this, perfect symmetric, and it would go to a maximum at 50-50, sorry, at 50-50. So, and omega is a single omega for the whole composition range, and that if you give a particular value, any value to it, then you can see that the maximum value of delta H mixing. For example, if I take a simple case like I take XA as 0.2, then XB is 0.8, am I right? Then XA into XB is how much? 0.16. So, if I take 0.2, 0.8, then the XA XB is 0.16. If I take 0.4, 0.6, XA XB is 0.24. Only when I take 0.5, 0.5, you would say it is 0.25. Only then this is the highest. So, that is why the maximum value or the minimum value of delta H mixing, depending on whether omega is positive or negative, is only at 50-50. At 50-50, the delta H mixing will either go to maximum or go to minimum, provided you will have omega positive or negative. When does it not go to a maximum or minimum? When omega is 0, as simple as that. When you have an ideal solution, then when omega is 0, then obviously delta H mixing is 0. So, that is a very remote situation, we are not considering that. So, we are looking at omega being positive. First and foremost is when do you get a miscibility gap? When omega in the solid is positive. This is very clear, all of you, I think this is very clear. Then the next question is, what is the temperature at which you get this maximum? If you want to look at that, then obviously we said one easy way to look at it, which is what many of you have actually done, but at the same time I said the correct way of doing it is another way which many of you have not done. So, I said the easy way is to see what is the free energy. G is XA XB XA GA plus XB GB plus omega XA XB plus RT XA ln XA plus XB ln XB. This is the final formulation that we have. If that is the case, we said in principle it is a combination of delta H mixing and T delta S mixing which is going to decide this, we said, and as a result when T delta S mixing dominates the delta H mixing, that is when you would see that miscibility gap closes. So, and we said if you can assume these as standard states and assume it to be 0, GA and GB. If you assume GA and GB to be 0, basically you equate these two, and that is one crude way of doing it, and then equate these two, and if you look at omega XA XB is equal to RT XA ln XA plus XB ln XB, and then equate these two and find out that T where this is equal. This is a very simple way of doing, but that is not the accurate way of doing. The accurate way of doing is when binodals meet, when the binodals meet at a particular point, and when binodals meet also the spinodals also meet. So, you should find out that particular composition and temperature where the two spinodals are basically meeting. And what is the definition of a spinodal? Yeah, second derivative of the free energy is 0. So, basically take this expression, find out the second derivative and equate it to 0, and you would find that particular, and again put one boundary condition there that I am assuming XA equal to XB, because I know that this would happen at 50-50. of course under situations where it is following a regular solution model, because we have already assumed that it is a regular solution model. Once we assume that and then put a condition that it is happening at xa equal to xb that equal to 0.5, and then you would get an expression which is what actually Tc equal to omega by 2r. If you do this you will not get Tc equal to omega by 2r. Many people have done this up to this and then put t equal to this this divided by this and then finally said omega equal to 2 Tc equal to omega by 2r. How do you get from there Tc equal to omega by 2r? You will not get, just because you put xa equal to 0.5 xb equal to 0.5. what are you going to do with ln x 0.5? So ln 0.5 does not give you the value that you are talking about. So let us try to do that for your benefit today and then see whether this really happens, and you would see very easily that it happens. Let us look at the first derivative. I hope you people still remember your maths. So first derivative for this, before you all do that we should try to see there is one more boundary condition in this. What is the condition that we know in case of a binary? Xa plus xb equal to 1. So I can write xa always as 1 minus xb, right. So wherever xa is there you replace it first with 1 minus xb. Am I right? So we have simply wherever xa is there we have put 1 minus xb and this things like that, and once you do that now you do the first derivative. We do it with respect to b, you can do it with respect to a also, and then there wherever xb is there you can put 1 minus xa, it does not matter. Usually we consider b as the solute, a as the solvent, and then we are doing it with respect to xb. And if you do this, this is ga minus xb ga, okay. So ga is 0, derivative of a constant is 0, that much I hope you still remember. So this is minus ga, this is minus xb into ga, so it will be minus ga derivative, and then this will be plus gb plus, here there are 2, okay. So it is xb minus xb square, so omega into xb is 1, derivative of xb is 1, xb square is minus 2 xb, am I right? And now you look at this, this is a little more complicated. Ln of 1 minus xb is there. So what we simply do is we change the derivative here to 1 minus xb. The way we can easily do it, whenever you want to do dou by dou xb of ln x 1 minus xb, if you want to do, you can simply write it as dou by dou 1 minus xb, okay, of ln xb, ln 1 minus xb into dou by 1 minus xb by dou xb. I can always write like this. So this I am dividing it into two parts, so that this is easy for me and this is again easy for me. So instead of change dou by dou xb I am taking, I will take dou by dou 1 minus xb. Once I do that it becomes very easy that this will become, I will do it in two parts. First I can keep this and then derivative of this will be what, minus 1, am I right? 1 minus x b derivative is minus 1. So that means this is minus ln 1 minus x b, that is 1, and then I now keep this and then take derivative of that, take derivative of this is what, 1 minus x b, 1 minus 1 by 1 minus x b, this is the derivative of this, this part, and the derivative of this part is minus 1, am I right? The derivative of this part is 1 by 1 minus x b, ln of anything is 1 minus. So a derivative of this is minus 1. So this is minus 1 by 1 minus x b, and if I do that, okay, and this I am basically keeping this constant, so that would become actually minus 1, because this 1 minus x b divided by, I mean multiplied by minus of 1 by 1 minus x b. So it gets cancelled, so you get minus 1 there. So this whole part is simply this derivative of that. Is that clear or still some doubts? And then the rest is again x b, you keep x b and then derivative of this is simply 1 by b, so it is plus 1, and keep ln x b and do this, so plus ln x b, this is what it is. So plus 1 minus 1 goes off, and you have ln x b minus ln of 1 minus x b, this is what you would get, and that is what is going to be the final expression. The final expression for that is, if I say dou g by dou x b is equal to x g b minus g a plus r into 1 minus x 2 x b, right, plus r t into ln x b minus of ln 1 minus x b. This is the first derivative. Once I know this is the first derivative, I can easily do the second derivative, dou square g by dou x square. If you do that, this and these terms cancel, these terms will vanish because it is derivative of a constant which is 0, and then this, it is omega, again it is constant, so minus 2 x b is minus 2, so this is minus 2 omega, the derivative of omega minus 2 omega x b is minus 2 omega, plus r t into ln of x b again is nothing but 1 by x b, am I right? 1 by x b minus ln of 1 by, okay, so again 1 by 1 minus x b, and because this is minus and you will get a minus there, so that will be plus. So this is what you would get, and this is what, if you equate it to 0, you will see I have never done these derivations for you, assuming that you all can do it. So you can see that basically 2r 2 omega is equal to r t into, okay, if you take it so it is basically 1, am I right? If you do LCM there, you would basically get that. So that means t is 2 into omega into x b into 1 minus x b divided by r, that is what is the TC. Solves the problem. You put x b as 0.5 and you see this is 0.5 into 0.5, So 0.25. So you would see that Tc is omega by 2r. What are the assumptions in this whole derivation? Regular solution model, and one more assumption. Yeah, we are assuming that the spinodal or the miscibility gap closes at the middle of the phase diagram. It is an assumption. It need not, but in a number of cases you see that, provided your phase diagram is a simple isomorphous and there is nothing else on the other sides. In a number of cases you have a miscibility gap. If you go back and see some phase diagrams, you have miscibility gaps only in a certain region, rest of the region you have possibly intermetallic compounds and things like this. This is really a fascinating thing, that you have an intermetallic compound in a phase diagram, you still have a miscibility gap in certain region. There are a number of cases. I want you to simply go back, if you are interested, see Masalsky for example. There is 3 volumes of phase diagrams. Just go through, you will see a few phase diagrams that basically tells that this itself is wrong. Assuming that you have a regular solution model, regular solution model basically assumes that the interaction parameter is the same from one end of the phase diagram to the other end of the phase diagram, which is actually not true. In fact, it is not true in all the cases where you have intermetallic compounds, whether you have a miscibility gap at all or not. The fact that you have an intermetallic compound in a phase diagram indicates that at a particular composition there is a strong negative interaction between A and B, otherwise you will not get an intermetallic compound. So that means at some other places, other 2 sites, for example you take iron carbon Fe3C, at 6.67 suddenly you get Fe3C. You do not have any other compound in the whole of phase diagram up to 6.67. So that means that there is something special happening at 6.67, where you have 3 atoms of iron and 1 atom of carbon. Suddenly such a configuration, you see there is a strong attraction. This is true with other compounds also. If I take gold copper, CuAu, you have 3 compounds we talk about, AuCu, Au3Cu, Cu3Au. That means at 3:1, 1:1 and 1:3, these 3 compositions you have an intermetallic suddenly, at no other compositions you have. That means at other compositions the interaction between A and B is not as strong as at these compositions. So that basically tells that omega is not really constant at all compositions. And in other cases also, which I have told you earlier, for example copper zinc, if you take as an example, we see that zinc dissolves in copper to a large extent, whereas copper does not dissolve in zinc, less than 1%, whereas zinc solubility in copper is almost 40%, 38% or so. So this basically means the interaction between the copper and zinc on the copper side is different, and on the zinc side is again different. That is the reason why people had to go to subregular solution models, and wherever intermetallics are coming into picture, people do not use neither of these regular or subregular. We have what are called other models called cluster models. So you assume that there are clusters inside the material and try to look at what is the, you assume all kinds of clusters, 1:1, 1:2, 1:3, all kinds of possible clusters that I can think of, and then try to calculate the free energy of each of the clusters and see which clusters have a lower free energy, and those clusters will be the ones which are stable. If all clusters have the same equal free energy, that means we say that that particular system would prefers to be an isomorphous system, because there is no special attraction for any particular cluster in a particular system where let us say the it follows a ideal solution model. Let us say in such a case, if I calculate all the possible clusters, you can find out innumerous stoichiometries you can consider, 1:1 to 1:100, whatever you want to consider. So all possible combinations, if you start calculating the free energies, and if you find that all of them have the same equal free energy, that means in principle you do not have any compounds. If there is a particular compound which gives you a much lower free energy, that means that particular compound is the one that you will observe, rest of them are all equal free energy. So that is how people actually calculate using cluster variation model, and then see whether you get compounds or not get compounds. So that is how we do it. So this is a way to calculate, and this is the same solution whether you are calculating the Tc for the spinodal, because you know in Tc for spinodal basically means the two spinodal points are meeting at that particular temperature, am I right. So that means again it is the same, clear. So I want you to remember this, and when you want to do it next time you should be clear about it. Okay.
Sir, omega fundamentally represents what? Is the elastic misfit that is causing the matter?
Omega fundamentally represents what is the attraction between A and B. For example, it is more related to you know more related to the valency mismatches. For example, sodium and chlorine, one with a 1 electron less and another with a 1 electron extra. So you have an ionic bond coming into picture, right. So that means because of this this particular sodium wants to stabilize its configuration by taking some other electron, let us say. So it tries to combine with an element which has one excess element electron. So it tries to look for which are the ones which have, and once you put the other element in combination with sodium, you suddenly form a compound. H2O is another example of that. So all compounds basically are related to their electronic configurations. At the same time, when you are talking about intermetallic compounds, in addition to electronic configuration, there is also a size effects that come into picture. They may want to form a compound, but when the second element is sitting inside the lattice, there may be so much of a strain that is going to counteract the chemical affinity between A and B. So as a result, you may see such a compound may not form, though electronically it would like to form. So it is a combination of both the factors. We cannot just say it is size factor. Okay. In fact, there are a number of what are called size factor compounds also. They have nothing to do with the electronic configuration. Just because the size of the B element is such that it fits into the voids. For example, there are a number of A to B type of compounds. Most of the A to B type of compounds are all what we call them as size factor compounds, where the second element fits into the lattice of the first element somewhere, so that it forms a good compound. So there are different types. So you have to consider each element carefully and then look at it. And when you look at different elements, for example, Mg2Si is one such example, is a size factor compound. You do not see that in every other things. Al2Cu is also another, which is to some extent a size factor type of a compound. So it looks at aluminum and copper atomic sizes, where they go in. Of course, they are more of substitutional, but their atomic sizes are such that aluminum is much bigger when compared to copper. So you have to look at the, in fact even the whole bulk metallic glasses also people are talking about in terms of the size factor. They say that if I can take a one element with a bigger atom, another element with a smaller atom, then the smaller atom fits into the bigger atom lattice and makes the whole packing very dense, and the moment dense packing is obtained, then the structure is more stable. So whichever makes such a dense packing possible, you would see such a thing is stable. For example, the best zirconium based bulk metallic glasses are zirconium beryllium. The best iron based bulk metallic glasses are iron boron. One is a very small element, another is a bigger element. Zirconium beryllium is another. Palladium nickel phosphorus is the bulk metallic glass with the highest what is called critical diameter, almost 70 millimeters people have found. Palladium nickel copper phosphorus, again phosphorus which is very small there, it goes and sits into the palladium lattice and then makes that stable. Incidentally, if you look at even the phase diagram also, palladium phosphorus, you get the best, there also there is a critical amount of boron, which when it goes into the lattice the structure gets stabilized, and that is what people calculate. For example, iron boron, if you look at it, 20 of boron and 80 of iron is the one where you actually see this is happening, and that is the reason why if you look at iron boron phase diagram, you have a deep eutectic at 80-20. Same thing, palladium phosphorus, you go to and see palladium phosphorus phase diagram at 80-20, you have a deep eutectic. That means for such a configuration the liquid will have a high density and such a liquid gets stabilized, and once it is stabilized, obviously once the liquid is stabilized, glass is stabilized.
But will that not lead to the incremental component?
It need not, because the question is whether it would like to form a regular configuration or it would like to have a randomly sitting and then giving you a high dense random packing. We call it as dense random packing. It is dense, but it is a random packing. So such kind of structures are all there. There are so many liquids. That is why we say bulk metallic glass is that where the viscosity is very high. Viscosity, why is it high? Because it has a dense random packing. So you put those elements, that is why not every 2 elements, just because for example I take some multi component system 5 elements, it does not mean that every 5 elements if I choose I will get a glass. For example, we are working on what are called high entropy alloys. In high entropy alloys we do not get a glass, we still have 6 elements, you can even put 8 elements, it does not mean that it will give a glass. So just because you have more elements, so that is where you have to look at whether they have a strong attraction first of all, because liquid gets stabilized only when the delta H mixing is negative. So that is one you should look at, whether A and B and all these elements when you put them, what is the overall delta H. See, for a binary I can easily talk about one omega. How do I talk about a omega for a quinary system or a hexanary system? So I have to consider individual interactions, multi component interactions. So this is a little more involved calculation, but one can do it if he is interested. Second is look at size factors again. We know that you would get a glass whenever the size factor is greater than a certain number, so that solid solution is not preferred. We know from Hume-Rothery that when the size factor is less than something you get a solid solution. So all those conditions which would prefer a solid solution formation would lead you to a high entropy alloy without being it amorphous, and all those conditions which do not encourage, which are not conducive for a solid solution formation are the ones which would lead you to a glass provided you have a multi component system. So that is why it is it involves a lot of thermodynamics to understand why, for example in a multi component system, in a 5 component system, how do I know which is the best composition for me to get a glass? In a binary also, for example if I look at the phase diagram, I can say, oh, at this composition I have a eutectic, because I have a eutectic I can say yes, it would form a glass. In fact there are many interesting cases, I would show you one. If you have a phase diagram which looks like this, okay, okay, let us look at this. Take a case like this. Take a case like this. It has 2 eutectics. Any example that you know? Mg2Si, very simple. If I take this system, there is a Mg2Si at the middle. Let us say, if I cool this very rapidly, and Mg2Si being a compound, you need atoms to sit in specific positions, and that is not, time is not allowed for such a thing to happen. So what happens is Mg2Si cannot come out. Then what should come out? The liquid would remain as liquid, and it would remain as liquid until you, if you extrapolate this liquidus curves to a particular point where you have another eutectic, which is what we call it as a metastable eutectic. So in a phase diagram, if there is a eutectic, a normal eutectic like iron boron, I can say yes, that is a composition where you can get a glass. But if you see things like this, if you start thinking that this is not forming, what is then going to form? That liquid at that particular composition is going to be undercooled continuously, until you reach this temperature. And so that means in this alloy, though the two eutectics are shallow eutectics, still this this particular phase diagram can give you a glass. Though I may say that, sir, if I do the T naught, the T naught is not really very sharp, not very deep, it is shallow, but in spite of that you would see that you will get a glass, because if this is removed then you get a different metastable phase diagram, and in that metastable phase diagram the eutectic may be very deep. So this is how you can see, the moment you see a deep eutectic, whether it is in the stable phase diagram or in a metastable phase diagram, then there is a tendency for the formation of a glass. But this is easier to see in a binary. How do I see it in a ternary? How do I see it in a quaternary or a quinary or in a hexanary? So that is where you need to do certain calculations to find out which are the compositions where the delta H mixing, for example, is highly negative. So you try to calculate the delta H mixing for the whole multi component system and find out where it is negative, and also find out which is the composition where you have the size factor being highly positive. What is the where do you have the highest size factor? In a normal binary system, where do you usually get a highest size factor? It is usually at 50-50. Whenever I put B into A, the highest misfit comes into at 50-50, provided both are substitutional. That is where the you will have the highest strain. That is the reason why you would see miscibility gap more or less will go up. You need a higher temperature to overcome that misfit, to accommodate that misfit. That is the reason why the Tc is lower here, Tc is higher here. This is the Tc for this alloy, this is the Tc for this alloy. So at 50-50 you have more strains, so you need higher temperature to accommodate those strains, so that you get a single phase solid solution. So similarly you would see that in a binary you can say it is at the highest. What about in a multi component system? So you try to calculate where is this size factor going to be the highest, and then look at these two combinations. One is which is a simply chemical interaction, another which is a topological interaction which is a size factor related, and see a combination of these two, and people do all these calculations. We ourselves have been doing it, and if you are interested, it is a very fascinating field to, and then do an experiment later, identify that composition, do an experiment later, and then see whether that works out correctly or not. So this is how people regularly do to identify that. Okay, any other question? The other point I think which most of you, yeah, the only point in the errors in the phase diagram which we discussed I think in one of the classes, where the phase diagram which looked like this, so this error many of you could not, by that time possibly you did not know, but after the class I think we discussed. So now I think by now you know this. That is it. I think rest of the things were easier and many of you have answered it. So I think we will leave this. If there are any further questions, please feel free.